So thank you very much for the invitation, Rob, to talk to everybody today. And I'm going to talk to you about this project called Repoint, which stood for redundantly engineered points. And the idea of the project was to try and make track switches and turnouts a little bit more reliable. We've got a lot of issues in the UK, so I'll tell you a bit about some of the issues, what we've been trying to do with the project. This project's quite a long running project, so we've actually been working on this myself and colleagues since about 2011, so it's a long time, a bit too long possibly. Sometimes I wonder whether when I write next generation track switch I should put a question mark after it. Maybe you can tell me at the end. So a little bit about me and Birmingham University, but a very little bit. So we're in the centre of the UK, more or less, at Birmingham. So it's a very little island compared to Australia, but Birmingham is right in the middle, which is great in many ways for getting around, but it's a bit of a nuisance for someone like me. I grew up in the northwest, close to the coast, and I struggle with the fact that I've lived for 30 years well away from the coast, so I miss the seaside. But it's a good place, Birmingham. It's one of the leading universities in the country. And a bit about my background. So I studied as a mechanical engineer initially, and then I studied an MSc in mechatronics. And I've stayed interested in that space between the different engineering disciplines, really. Did a PhD in control systems, worked as a professional engineer for Alstom in power generation, and ships and all sorts of things that we got involved in for 7 years. So I was really lucky there. I had some very interesting roles, and then moved to Loughborough University, which is not so far from Birmingham, but is a small town that if you didn't happen to spend some time near there, you'd never have heard of it. So I was there 17 years as a senior lecturer, then a professor, and then I moved to Birmingham in 2018 when more of my research was becoming rail oriented. And Birmingham has probably the UK's leading railway research and education centre, so it seemed sensible to come there. So a bit about my interests. So I'm obviously interested in control systems engineering, a thing called fault detection and condition monitoring. So these are linked. About an hour. So these use some of the tools and technologies that control systems engineers use, but to detect things going wrong and reconfigure things, and the mechatronic systems design really is at the heart of it, and Repoint really fits in that space. So why I like those areas actually is that you get to apply it to just about everything that you can think of. So I've worked a little bit in automotive, on rail, obviously, construction industry, automating piling rigs and stuff in the aircraft industry, in the power generation, some nuclear fusion experiments that we do in the UK that have helped develop some systems. So I've had a charmed 30 years or so doing all this stuff. But what I'm going to talk to you today about is this Repoint track switch project, which has been ongoing for quite some time. And it started out because of this problem specific to the UK, but actually it's a problem that you find around the world with slightly different metrics and measures. So this is a lot of miserable people stood on a platform wondering where the train is. We have quite a lot of delays in the UK, sadly, and even more sad or good news when I started this project, I suppose, in a weird way, is that about 25% of them are down to track switch issues. So we have 500,000 delay minutes in the UK caused by track switch faults, and it costs us about £49 million, or it costs Network Rail £49 million in the delay payments that they have to make to the operators that sometimes the operators pass on to the customers. So it's quite an expensive business, and I think there should be another figure there. Yeah, so we're also spending around a fifth of the maintenance budget each year on keeping the track switches working as they are at the moment. So we've got an awful lot of delays caused by these things, even though we're spending a fortune maintaining and inspecting them to try and minimize that. And I'll try and tell you a little bit about why that is, but part of the reason is that they've been broadly the same since about 1909, when the patent was filed there, and they basically slide across like this. But the critical things are you have to unlock the switch when it's requested to move it. Once it's got to the rail that it's moved towards, you lock it again, and then you report detection to the signaling system. And if any of one of those elements doesn't work, then you stop the trains. The signaling system will stop the trains, and we wait until the maintenance guys hop in their van and go and find out what's wrong. So a single fault in any of those systems causes a delay. And of course, as I was saying, to avoid that happening too often, we're spending a lot of money on inspection and maintenance. This is quite an old, and I think this one is a video from a switch in India. So I've really struggled to get decent video footage of switches actually actuating. So I've got a nice picture on the next one, but this one won't move. It's a similar switch, and the switch machine, or what I would have called an actuator before I started learning about track switches, is sat on the box off to the side. And if we take the lid off that, or a slightly shinier, newer version of that, then you get to look at a system like this. So we've got a motor at the top, a gearbox, a complex mechanism in here that allows actuation to be done through this rod. And then once you've actuated across and the switch blade has hit the stock rail, that disengages and engages the locking mechanism that's down here, so that the lock is moved in to lock the system. And then the two rods right at the front, which you can see right at the bottom of the screen, actually are connected to a mechanical detection system here and some electrical contacts that tell the signaling that it's been detected or not, and which position it's in. So there's quite a complex thing, and I sort of looking at these. Obviously, there are different manufacturers, but they're all broadly similar in terms of complexity and typically look like the inside of a Swiss watch. So it doesn't really surprise me that stuff goes wrong. They're very mechanically oriented, which is okay, but we have got all sorts of electronics and other approaches these days that if you didn't know it needed to be like this, you might design it differently. So that was really what we set out to do, was okay, if you don't know that track switches, or the mechanism to allow a train to transfer from one route to another has to look like the ingredients that you might find in Network Rail's specification to produce a track switch. If you don't know that it's going to look like this thing up the top right, how might it be? And we spent actually about 2.5 years pondering that question with lots of industry stakeholders and people who weren't industry stakeholders, who didn't know why things were as they were and weren't brought into the history. And we generated a whole range of ideas, from some of the daft ones where we had little ramps and the trains jumping from one track to the next, to more sensible things. I think someone proposed trained squirrels to remove the ballast from between the stock rail and the switchblade and all sorts of things. So we evaluated those. We threw away the really silly ones. Some of the silly ones inspired better ideas, and we put those on the list. And eventually, after a couple of years, we ended up with two main ideas that we thought might go somewhere. And the first was about the actuator bearers. So we wanted to be able to use redundant actuation like you find in the aerospace industry and in power generation plant, where often you'll have redundant actuation and you'll also have designs that can fail safe if they do fail. So we were trying to do that with the track switch actuator. Part of the biggest challenge there is with locking, which is a single point failure, and having two switch machines wouldn't enable you to unlock the second switch machine if the first failed. So we had to redesign and rethink the actuation, which we've done. I'll show you a bit more about that in a minute. We also thought we could team this up with an idea of using something that looked more like a stub switch, which there have been these used a lot in the past, but we wanted to actually have interlocking between the ends of the blade on the stub switch, and I'll show you a picture of that in a minute as well. So that actuator bearer, if we took a slice through one and did some PowerPoint engineering, so this was probably about 2014 or so, when this grey system at the top here with the rails on is down, it's locked and can't move sideways. You unlock it by lifting it up and then move it across to the new position and drop it back down, and gravity and the spring force of the rail and in the limit the train set on top of it keeps it down and locked. So when it's in the down position, you're locked laterally. When you lift it up, that unlocks it, and that means if you had 2 or 3 of those in parallel and the grey part is attached to the rails, then these could be not turning on the middle one, and the ones either side could be doing the job of unlocking and moving the switch. So that's the principle, which seemed fairly obvious once we'd thought of it, but wasn't all that obvious because it took us a couple of years to come up with. The interlocked stub rail ends, they need to look a little bit, we thought, like an expansion device to the wheel as it goes over this joint. This isn't a very good picture of it, but it is one of the better ones I've got at this stage. And actually, I'll show you a picture a bit later that's better, that shows you the two detached. So they kind of lock together as well, so that the top one slots onto the bottom one and they can't move laterally when they're in the down position also. And I think another picture that will come up later will show that better. So we had a look at those concepts, and we went back to some of the requirements that we'd set out for the project, and we worked out all sorts of benefits, and it depends on the location and all that, what the actual benefits would be. Is it high speed? Is it in a station throat? Is it, you know, so the picture changes, which is one of the challenges with making a business case. But I suppose the really key things are that this passive lock allows you to make use of redundancy. That allows the reliability improvement, and then you can tolerate failures now, which means that you don't have to rush out and fix it the moment it breaks. So you can actually schedule your maintenance, and you can tie it in with condition-based maintenance and condition monitoring and such if you like. So we had that initial idea, and a couple of years later we got some funding together and we managed to build this model in the lab. So this is scaled for a little scale railway that operates. It's called the Romney Hive and Dymchurch Railway, that's in the southwest of the UK, and we got 3 routes going out from this stub joint and a kind of giant Meccano actuator with it all working, just to demonstrate the concept really and try and get some enthusiasm for the idea. So we had a lot of people come and look at that. We only had the budget to build one of the actuators, so we drew the other 2 on the floor and some pretend rails, just to try and help people picture it. And at that point we got quite good buy-in from the RSSB in the UK, so the Safety and Standards Board, and they liked it, and with them and Network Rail, we managed to get some government funding and the go ahead to build a whole switch panel. But they said, could you build the actuators and apply it to a conventional switch, because they thought having those two innovations was a step too far. So I'll tell you a little bit about that. Yeah, in the whole thing, we were looking at all five of those aspects. I'm just going to talk briefly about three of them, just to give you an idea of some of the things we've been doing. So from the sort of engineering and mechatronics, mechanical design side of things, there's of course a lot of options for making this cam mechanism. The one that we built first in the lab was like this, a rack and pinion system driven by one motor. There's options where you have two independent motors driving two gearbox and cams, and you link them together electronically. There's options with pulley wheels and belt driven actuators. And so we looked at a whole range of possibilities. And then again, we got the stakeholders in, and how do we select those? So we considered things that our industry advisors suggested, like the obvious things: reliability, maintainability. The one at the bottom, I've put an exclamation mark after it, because I wonder why on earth I agreed to include that, or all of us agreed that as a team, that we should judge it based on whether it would be acceptable to the rail industry, which looking back now seemed a silly thing, because some of the aspects people said they just weren't acceptable, but for no good reason really. So we went through a process, we ranked these. This is a thing called the Pew matrix, which if you ever get to design things and try and pick between different options, quite a good way of sort of documenting your thought process and why you like one and not another. We picked the double motors connected electronically together, and decided to go that way. So we then went through the process of actually engineering those and working out what the motors might look like. Could we fit them in actuator bearers? And that actually is one of the biggest challenges. If you don't want to make the bearers significantly bigger than a standard network rail bearer, that people have quite fixed ideas about the size of a standard network rail bearer, but they can't actually give you the dimensions of it. So we agreed some dimensions eventually, and we designed it all to fit in there, and it all looks a bit like this. So it's a bit more complicated than the PowerPoint, but you can see the cams and the locking sections a little bit, the locking blocks here, and then there's another locking notch there and one on the other side. So we went through all that thought process, and in parallel we built some simulation models. So we built a simulation model of the actuator and the switch and control panel. We also did some dynamic simulation to look at what trains would see as they pass over those joints. So we're using Vampire and Simpac usually in the UK. I think, I don't know what you use in Australia, but there'd be some similar packages that people use to look at the wheel rail interface. And then this one's more about the electromechanical design, so the model of the motor system, and then some finite element beam bending equations to look at how the rails bend and move. And because we'd built one in the lab, we were able to look at that, compare it to the model of the electromechanical actuator, and just validate things. So are these models we're using reasonably useful? So we collect the current data from the motor here and the position that in meters of the rod in this case, the rack, sorry, and the velocity of the cams in here, and we plot those against the measured ones, and we go, okay, well, our model's not so bad, maybe we can use that in the prediction. So what we did before we began to build this switch panel was built a complete dynamic model of the whole thing, including the control system that was going to be on an NI National Instruments embedded processor system. A bit of overkill for what you need, but quite good in our case, because we wanted to collect a lot of data and see how the thing performed. So we modeled the beam bending equations of the rails. We model the actuators in each of these three actuator bearers. We got the detection, so we had two lots of detection, one for each rail at each bearer. So in the end, 6 signals that we consolidate together to eventually give a normal or reverse signal over this side. Oh, and the command comes in over here. So we built the whole thing in simulation and checked it all out with the coefficients of the real motors and gearboxes and everything, so that we didn't want to run the risk of buying components, putting them all together and they don't work. So we checked it all out in simulation. These days you might call that a digital twin. I don't know. I'm not so keen on the name. Oh, and that's the interface. I spoke about that. So then we begin to order the components, and this is the first one that we've built in the lab. So we got the hollow steel bearers from a company called Progress Rail that are in Nottingham, so not far from us, and they sorted those out for us. Actually, I think we painted them yellow ourselves because they looked a bit rusty when they were delivered. So we sorted them out, painted them up yellow, put the components in, and we began testing it all. So if we zoom in on this one, then here, and we just check the electronics out and that the control system controls those cams to go from one angle to the other in a nice smooth way, and that the two are synchronized, which they need to be. Because, as I say, we've gone for independent motors. The link between the two is in the electronics in this particular system. So we get that working. We put some bits of rail on top and we check that it still works, and then we make 2 more, and then we go to Progress Rail at Nottingham and their car park, actually, where they set up a little switch panel for us. Not so little, it's a C switch. We call it in the UK a C switch, which is the most common length of switch that we have. And we put the 3 actuator bearers in and we test all that out. So we got the LabVIEW software that does all the control code and records lots of data for us. And we find that we can bend the switch rails quite nicely. So at that stage, we're quite happy. We did have a couple of little glitches as we commissioned that, like you do in engineering. And we managed to get a little bit more funding to say, well, let's take this and put it somewhere. So we went to the Great Central Railway, which is in Leicestershire. It's actually about 5 miles from where I live, near Leicester. And they had this little siding that they use occasionally, but not too often. And they had quite an old switch panel in there. And they said, yep, you can replace that. So we got it all on the back of a truck and took it from Nottingham to near Loughborough, stuck it in there, and it's their nicest bit of track still, I think. Assembled it all. We got the 3 actuator bearers. So any one of these, we tested them independently, can operate the switch mechanism by effectively lifting and unlocking the other 2. There's a lot in the line side cabinet, and in a real production version you wouldn't need all this. You certainly wouldn't need a laptop. We didn't have a signaling system here, so we'd got everything in place to interface it to the signaling, but we had to do it from the laptop to be able to actuate it. And it all worked quite well, and we were going to test this in the summer of 2019, and in the end it ended up being in the winter over Christmas, so it got quite a good test of rainy, snowy, miserable, cold conditions for about 2 months that we operated it. And of course then we ran out of money. Toward the end we had a big event where we invited a lot of the UK industry to come and have a look, and they all got very excited, but they said, we like it, but we prefer that stub joint version. We think the benefits come from having a stub joint. So that was a little bit frustrating, because at the beginning they told us that you have to apply these actuators to a conventional switch for it to be acceptable to us. This isn't a real Network Rail person. So they want us to replace this with something like this. So we've spent probably the last 4 or 5 years working on a project to try and do this. So I've got a crudish video. So we got now the stub joint just with 2 routes. So it's going to be a C switch again. So it'll occupy the same space and the same more or less profile, but without those long plain down switch blades and with this little interface up here, which again have better pictures coming in a minute. This animation is a bit of a crude thing, so it doesn't actually lift and move in the animation if you're looking really carefully, but it does in real life. It has to lift and move. So again, funding is always a challenge in universities. So we've managed to get funding to test out this part of it, sadly, only. So we repeated all that design process, the optioneering and everything all over again. And this time there was some dislike of the particular hollow bearers with the open tops. So we're now using a standard dimension steel channel and cutting out these bits to make the actuator bearer housing. Slightly different gearbox and motors to fit in this smaller dimension. The stub rail ends that my colleagues are just checking fit together there in the lab, the control system, which we build up all over again, and then we put it in the lab, and it ends up being something like this. So this is what we've got. If you come to the University of Birmingham at the moment, this is how far we've got, and we can show you this. So this device is, of course, just the top part of the picture shown in the top right. So you got to kind of use your imagination. And in fact, to try and help me show other people, I kind of mangled together this photo. It's quite hard to find, again, a turnout where you can crop the right bit of the photo, and the profile's about similar to the photo angle I took in the video that we took in the lab. But this gives you an idea. So when it's over to the right, you're going out on the turnout route, and when it's on the left-hand side, as it was about to be, as it is now, you're going straight on up there. So this is where we are at the moment. And in terms of what we're doing and the journey that we're on, I think we've almost done all we can. We've just been awarded some funding to build another of those actuator bearers, because yet again, we've just got one of them. And our big selling point is the redundancy. We know that will work, but we need to demonstrate it probably in the lab and then out on a real railway. So we've got an initial bit of funding to do that in the lab. And if we look at kind of where we've been, it is a depressingly long journey. And I think looking back with hindsight could have been a bit quicker. So, we came up with all those ideas and did the basic lab demo and patented it in about 2016 or so. Then in 2018, moved the IP and the patents and myself and key colleagues to Birmingham Uni, where we could get more support from the rail side of things. We demonstrated it on the video that I showed you on the Heritage Railway in around late 2019, early 2020. Network Rail funded us quite a bit to do the development of the stub joint, and we also did a lot of quite detailed HAZOP studies and things like that with colleagues from Network Rail. So part of the big cost of that is talking to a lot of people and looking at, okay, what might go wrong with this, what are the new failure modes that we are introducing as a system, and all of that, and figuring out how it all might work and how we feed that into getting a qualified system eventually. We got the Repoint Plus, as we've called it, demonstrated in the lab now. We've also found one of the big frustrations is that all of the industry players in track switch technology that we've talked to will say, this is great, we'd really like to be involved. As soon as you get a product that's viable, we like to get involved with you. No one really wants to support the next bit, which is putting a real one of these in track and not monitoring it for a couple of months like we could only do the last time around, but actually monitoring it over a long period of time with some carefully controlled traffic and gradually building up the use case and the confidence in it, and fixing the things that will go wrong when we first start testing this for real. There will be some things we haven't thought about that we'll have to change some aspects of the design perhaps. So now in 2025 we've just started a startup company to try and commercialize it. We got some funding from the UK government to do the next bit. We got some funding to do a feasibility for testing the whole thing at a test track that is under construction in Wales at the moment in the UK. And we're also talking to venture capitalists and all sorts of people, because actually in some ways not linking it to this new test track would be quite useful for us. There's some advantages to testing it at a test track, but they haven't built the test track yet, and we don't want to be waiting for that. So we're ideally trying to get onto a trajectory where by 2028 we'll have installed one for a few years, tested it, and with Network Rail gone through the process to get a certified product and product acceptance from NR. And then, as I've said somewhere, we got some patents. We got patents in a lot of the nations around the world, and we'd like to partner with people to exploit it. So we don't think we're going to be making track switches with our company. We're going to be partnering with the organizations that know how to make the permanent way parts, with organizations that know how to make and install gearboxes, and we're going to be helping them to integrate them and provide solutions using this technology. That's the plan. So with that, thank you very much for listening. I think that was about half an hour, which was what I promised not to go over. So thanks. I'm happy to take questions. I may or may not be able to answer them all. I've tried to list a lot of the people that have been involved. It's been a lot of people. If anyone's watching the recording and they were involved and they're not on my list, then feel free to tell me off.
Yeah, thanks a lot, Roger. I really appreciate you spending the time to take us through that journey. Any change is difficult, especially something as significant as this. It's a few people are clapping their hands. So yeah, there's a couple of questions in the chat already. So yeah, please feel free to put your hand up or to type your question into the Q&A part. I'll just go to them now, Roger, and I'll read out the ones that are already there.
Cool.
So David Stewart Smith just said, with the stub joint arrangement, how do you ensure alignment between the bearers on both sides of the joint?
Yeah, I mean, that is a very good question. So the bearers on both sides, if I can find, I've got a picture somewhere. Let's stop that from going in the back. So yeah, so with these two, because these are sat in the lab and actually we've not got the rest of the rail on, there's no real risk of them moving. But when you look at the full switch panel up here, so we're thinking one option is to use a bracing rail down the side here that extends across the joint. We've talked a lot with Network Rail actually over about whether, in fact, this is a more useful technology to use on slab track, where you'd be effectively building the bearers into the slab track, so that does the job for you. But it is important that these two in my video can't move relative to each other, so there has to be something, whether it's a bit like we've drawn here, or whether it's because you're embedded in slab track. You do have to think about that.
Yeah, no, good response, Roger. Thanks for that. John Paths asked, with a normal sliding switch, it pushes debris off the load carrying plates. Will this system lower the switch onto potential debris, resulting in an obstruction? I suppose.
Yeah, so there is a chance that it could. What we've tried to do, I don't know if you can see it so clearly on the video. So we've shaped the top of the stub joint so that ballast should fall off of that here, and it also provides a lateral resistance, because underneath on the other side of the top part that's coming down onto it, that's shaped to mesh with that. So we've designed that. The initial reason for that was to try and allow any debris that falls on here to be either falling off or be pushed off as you lower the thing.
Yeah. Roger, what about on the other bearers where it just lowers onto a plate?
Yeah. Okay. So down here. Yeah. So because, for example, there, that's a very good point. So you could get some ballast or some debris on there, and you would have an issue which is similar. I mean, we have, when we were talking about the problems with the plane down, the traditional switch blades, we had a lot of, I don't know if it was real evidence or more anecdotal evidence, that quite often you get ballast between the blade and the stock blade. And so part of this stub joint idea initially came from, well, we could avoid that scenario, but we create another one that you've pointed out. And
yeah,
so
you remove the risk of the ballast being of the debris being caught between the switchblade, but you introduce the risk of it being caught under the switchblade.
Yeah, you do. And is there a way? I mean, I guess we could put some covers over in the same way that we have with the actuated bearers. Probably needs a little bit more thinking about. If we're looking at slab track and there's no ballast, then maybe, I don't know, what is there other debris that's often getting on there?
I think things can fall off trains.
Yeah. Yeah.
You can get leaves as well, like leaf matter, etc.
Yeah, we know we do get leaves in the UK. Yeah. Usually they're in the paper for low adhesion events, but this is true as well. So that, I mean, this is part of really what we need to test. How big of an issue are those things in various different situations? I mean, some people will tell you that, well, okay, so it might not be completely down, but once the weight of the train's on there, it'll squash whatever's under there. Now, that, not sure that's a good enough argument. It would squash some things. It won't
squash a pinch nut.
Yeah, exactly. Yeah.
Okay, thanks.
Okay.
Thanks, Roger. There's quite a few questions coming in now, Roger. I'll try and put 2 or 3 together because they're all around kind of maintenance and wear. So regarding the stub joint, has it been tested under a load to replicate WRI fatigue test, and then similarly wear and track maintenance impacts considered in the design? Were any endurance tests conducted? And then Nathan's just, sorry, go on.
So the quick answer to most of those is that those are tests that we need to do. So we've got these stub joint designs. The designs we've done really have been mainly to make the wheel rail interface to allow this mating so that they won't move laterally to each other, and to make the wheel rail interface look like an expansion joint so that people can accept wheels running over this different kind of switch. What we haven't really done is analysed exactly how long that needs to be. We've done some FE, we've done some bending analysis in the FE software, but we haven't built and tested one with the weight of trains, or even under a machine where we can apply the loads that trains would apply. And there are things like on these bearing surfaces, you know, this interface will wear on both sides, and could be issues sometimes that if one route is used more than the other, that one will wear more than the other, and how big a deal is that? You can put special materials on there to make it wear less, but is that necessary? And so all of these things actually need thinking about, and in the end need testing. And this is one of the biggest challenges we have, actually, is getting sufficient funding and the ability to test these things, because it's big scale engineering, isn't it? And not easy to do in a lab.
Yeah, I suppose that leads on to one of Mike's questions. Have you considered existing tracks overseas for further development? And then can the technology be adopted on kinematic dynamic optimization turnouts?
Yeah, so we've talked in quite a lot of detail to people from Singapore Metro about maybe trying to develop this for them, but it would need to be not tested on their metro initially, for sure. I'm quite keen to try and test it in a freight yard somewhere, somewhere where vehicles are going slow initially, so we can test out some of the elements of it properly. The right place isn't high speed passenger transport scenarios, that's for sure, though in the end that might be the most useful place, but you definitely got to build up to that. There's some colleagues that I've been talking to in Brazil who a company called FASA, who are quite keen to help us develop this, and eventually they'd like to market and sell it in Brazil. There you're looking really at mostly it's freight transport, and mining. Big mining organizations own a lot of the railways and operate them out there, so there it's avoiding causing delays that result in you shutting down your mining operation and that kind of thing. And the business case is quite different in each case, and I think in some ways for me as a university, yeah, I'm an engineer, but I'm not spending my time steeped in railways. I struggle with all these different business cases and the possibilities, and actually at the moment we're trying to talk to all of these potential partners. We got some potential partners in Italy as well, who've just released a new type of track switch, but I think this might be the one that comes after that, so maybe in 5, 10 to 15 years time. So they're quite keen to talk to us, but we need to pick one and go for it and do it somewhere. If we could manage to go somehow with Network Rail and get certified in the UK with Network Rail, there's an advantage that a lot of organizations around the world are quite happy to adopt things that have been certified by Network Rail. So, but maybe the UK is the hardest place to do it, because Network Rail are quite tricky to deal with, because it's a massive fragmented company. So yeah, it's a challenge.
Have you considered going to the test track in Colorado or test tracks in Japan where they could actually install this and you could control the conditions for the testing?
Yeah, so that somewhere like the Colorado test track could be a great option, in the sense that I think you could even test these stub joints. You don't necessarily have to test them initially on actuated switch panels. You could just put a stub joint like that in and see how it behaves as trains pass over it, all that tonnage over several weeks and months, and look at the wear and those things. So I think doing something like that would be a really good thing to do. It's the cost that is the main challenge, because we're a university. We're now with a startup company, so if we could get some decent angel investor funding from a rail enthusiast out there who's just got too much money burning a hole in their pocket, then maybe we can go out and test that in Colorado, or as you say, in Japan. That'd be ideal.
Thanks,
I
Roger.
suppose
Yeah.
that's what we're trying to. So the guys on the team I'm on the technical side really, but some of the colleagues of mine who are picking up the startup company and who are looking at that, so they are starting to pitch to potential investors, and they're trying to push that forward. And I suppose one of my challenges is, as an engineer, I can see the advantages, but I can also see some of the challenges, and I'll be very honest about those. And you don't necessarily need to be too honest when you're pitching to investors. Bit like the garage mechanic who says, "Oh, I can fix it, but it's going to be expensive." Better just to say you can fix it.
Excellent.
Doesn't come easily to most engineers, that, I think.
Roger, there's a few questions going in the chat, but I'm just conscious of everyone's time. What I'll do, I'll
Yeah.
copy them all, and then I'll maybe send them in an email, and then whenever you get the chance, if you could respond to them, and I'll upload them to the PWI website with the presentation. That might be of use.
Yeah.
But there was one final question I was just going to ask, because I think two people have asked it regarding stress and unstressed track. So had the design been subject to thermal induced expansion within a welded track environment? So assuming the question is no, but has that been considered in the design? Is there any kind of
well, sort of, in the sense that this joint here that we're still looking at on the screen has been designed as an expansion joint, so that the two rails can move longitudinally relative to each other on there, and maintain a nice wheel rail interface. But somewhere down here you've got to connect to this, and somewhere up here. So I suppose partly we've considered it. So longitudinally these bits can move relative to each other, and it's okay. Exactly how much you need to allow for depends whether you've got some kind of joint near, as you come toward the switch, or whether you got welded rail going away.
Yeah. No, actually, yeah. Okay, well, I'll just say thanks again to Roger for spending his time to share with us today. It's been a great presentation, really interesting from my part as well. There's a lot of any change, like I said, is a challenge, and especially something like that is complete rethinking how we do track switches. So yeah, I think hands together for Roger virtually.
Yeah, thanks very much for listening. And
so I'll just
hopefully I can answer the other questions gradually, and people feel free to reach out to me if you got questions over the weeks.
Yeah, no, that's
thanks
great. Like
a lot.
We'll upload this to the PWI website in due course and get that. But just a few final slides from me just before I let you all get on with your day. As I've already said, membership to the PWI is important to us to support events like these and the other events. So please, if you're not a member, have a think about it, speak to your colleagues and speak to your employer maybe, and see if you can become a corporate member. So there's a few of the benefits there on that slide. There's also the corporate health plan that the PWI is also an offer there for members. We've also got the Rail Express partnership, so you'll see articles in there quite regularly. So that's something else we're expanding the exposure of the PWI. And then just what's up next, quite an important slide for us. So as you'll see there, next week we've got the PWI New South Wales special and technical meeting there. So there's some details on where that is. Again, please look at the calendar on the PWI website. We've then got the awards night on the 20th of February, celebrating the rail industry's finest people, projects and innovation. And then the golf days planned for the 28th of March. If you hover over those icons at the bottom, that'll take you directly to the Eventbrite, where you can get some tickets for those. So that might be of interest to some people on there. And then going forward, we've got the PWI Lunch and Learn plan for the next few sessions. Please have a look at that and see what if that's of interest to you. We've also got the PWI Executive Breakfast in May, so I don't believe the tickets are on sale yet, but Steve or Neil, if you're aware, that's still something that's in the plan. But if you go on the website, there's all the details will be there if you want to be part of that. And then, as always, a big thank you to our enhanced corporate members. They're all there, and then also to our valued individual members as well. So a shout out to all those people that are supporting these events and other events. And then finally, thanks to everyone who's joined us. I think I had 88 on the call today. Please keep giving your ideas. Please, I've seen a few emails come through while the session's been going on, so thanks for your input, and I'll respond to you there. Our next Lunch and Learn is on sustaining sleeper strategy, so that's incorporating what they've done on sleepers regarding composites, removal of timber sleepers, sulfur, concrete, and then lots of other things. They've done a lot of lateral resistance testing with other universities in the UK, so there'll be a lot of quite recent and up-to-date testing they've done there. So that might be a good session for anyone that's really track-based and interested in sleepers and where we're going with sleepers in Thursday. So yeah, I'll leave it there. We're just bang on the hour mark now. So thanks again to Roger. Thanks again to the group for joining us, and I'll hope to see you next time. Thanks all.
Thanks, Rob. Thanks, everyone.